Okay, so for the first multiple choice question, we know that an acid will produce a gas, referring to CO2 gas. In this case, when it reacts with carbonate. Okay, so we're looking for something that contains carbonate. B is the only one that does that. So I give you some information here, and I want you to write and balance this reaction. On the quiz, I will give you the actual formulas here, but we have HCl, it's aqueous, reacting that with calcium carbonate. Calcium is +2 and carbonate's -2. Just like we said above, because the H is going with the CO3, we're going to make H2O and CO2. Now, as an aside, when H goes with CO3, you actually make carbonic acid, but this molecule is very unstable and immediately forms this equilibrium between it and CO2. And in normal atmospheric conditions, it breaks down into H2O and CO2. So there is like this brief moment of time here where you are making carbonic acid. That's why when you blow or put CO2 in anything, you're actually creating an acidic solution because of that carbonic acid. And you're left over with CaCl2 in this case because the calcium is +2 and the Cl is -1. And I'm going to balance this reaction by putting a 2 there, and I think that's it. Mass of carbon dioxide, so we want to know the grams of CO2 here, and we've reacted that with 200 milliliters of 0.1 molar hydrochloric acid. So the first thing we need to do is get moles of hydrochloric acid. So molarity equals moles divided by liters. So we know that moles equals molarity times liters. So my moles is going to be 200 milliliters in this case, multiplied by that 0.1 molar, and I'm going to get 0.02. Actually, I'm sorry here. This should be 0.02 liters. And that's going to give me 0.02 moles of HCl, but I want grams of CO2. So I call this solution stoichiometry. Solution coming from the fact that we're talking about the concentration of that aqueous HCl. So I know that there are 2 moles of HCl every time I have 1 mole of CO2. This could have been just like PV equals nRT or anything else we do in stoichiometry. And I want to get the mass actually, so 1 mole of CO2 is 44 grams of CO2. And when I go through and do that, I forget what the answer is. Let's go look. That's going to be 0.44 grams. Grams of CO2. Okay. In this case, when we do the low battery, when we do the Lewis structure for that, we are going to get CO2 looking like this. And because there's dipoles pushing in both directions, this molecule is nonpolar. And because this molecule is nonpolar, whenever we have neighboring CO2 molecules, all I'm going to get in between there are London dispersion intermolecular forces. So because there are low intermolecular forces acting here, and this molecule is pretty small, so it has really low polarizability, the CO2 particles tend to not be attracted to one another, and they're really an ideal gas. They get expelled from the body as a gas. And you can write that out in a narrative or however else you'd like to write that. Okay, here we got this titration, and I tell you, they say that barium hydroxide is what's inside here, and we notice that it went from this level here, which is 12.6, all the way down to this level here, which is 35.8. So if you take 35.8 minus 12.6, we're going to get the answer here for this last one. Let me actually go ahead and do that. 23.2. in that case, so that makes the answer D. I think I put the wrong answer here. Let's go check. You have to be there. Not sure how that happened. Anyway, I'm feeling a little sick. So the answer there is 23.2. I'm actually doing the second one right now. And in this one, you put the indicator in, and we know that it's the flask actually down below where we put the indicator. So the contents go from colorless to pink. We know there's no blue red with phenolphthalein, but we know that the color doesn't change in the burette. It changes in the flask below. This one's bothering me. 35.5, 35.6, 35.7, 35.8. 35.8 minus 12.6. 35.8 minus 12.6 should be 20. Yeah. 23.2. All right. So 23.2 it is. All right. For this one, you're given the task of standardizing it. So you want to go through and describe the experimental procedure. I'm going to speak this one out, and you guys can write it down really slowly. So the first thing you're going to do is you're going to prepare your burette. You're going to prepare this 50 milliliter burette by rinsing it once with distilled water. You're going to then rinse it twice with this 0.1 molar titrant. After that's prepared, you're going to fill the burette, flick it out, and then you're going to get a certain volume of that acetic acid and place it in a 100 milliliter Erlenmeyer flask. So you're going to place a certain volume in here. Usually people place around 50 mils of the acid. You got your prepared flask up here. Okay. So then you're going to add a few drops of the indicator to that flask, and you're going to titrate until the indicator changes color. And then using the volume of the acid that you started with, the volume of the base titrant used, and the molarity of the base titrant, which is 0.1, you're then going to calculate the molarity. And that comes from this equation. You can indicate that if you like. Solution standardization. So there's some random multiple choices here. Remember, amphoteric means it acts as an acid and a base. It has to start with an H, so it can't be C, and it has to be negative, so it's got to be B. Negative allows it to be an acceptor of protons, and having an H allows it to be a donator of proton. Remember, an H plus is the same thing as a proton in this case. So describe the steps to prepare the burette. One, I said it above, you're going to rinse with DI water, distilled water. 2, you're going to rinse times 2 with the titrant. And then 3, you're going to fill that burette. And then flick to remove any of the air bubbles. Here, they're saying that the volume of the NOH solution was needed to reach the endpoint. With that, they want you to know what the molarity of it is. So normally what we do is we don't know the molarity of the acid, but in this case we don't know the molarity of the base. It's the exact same calculation. So here you're going to say 0.0571. Got that from here. And every 10 milliliters is equal to molarity of the base in 7.62 milliliters. Okay, and you're going to do that out. I believe you get 0.074 molar. You do that out. Let's go through and look at my answers I put down here for number 3, 0.075 molar. Now determine the mass. Okay, so molarity equals moles over liter, and moles will take us to grams. Okay, so we know the molarity is 0.074 molar, and that equals X over the volume, but this needs to be in liters now, 0.0762 liters, okay? And then that is going to give the moles of NaOH. So let's go ahead and do that real quick. 0.074, actually I'm going to do 0.075 because that's what I told you earlier, times 0.0, actually, this is 00, because 7.62 divided by 1,000 equals 0.00762 liters. 0.762. And so that gives us 0.0005 moles, 57 moles NaOH. And in every 1 mole of NaOH, there's 40 grams. So I'm going to times this by 40, and I end up getting 0.02 grams of NaOH. Okay, I'm going to pause this here for a sec. All right, so at the very end here, which of the following does not produce a gas? So we know a gas comes from H plus with CO3 2 minus. So that's going to be NaOH. All right, so let's finish these off. Okay, this is going to be H2O. And here I have LiF. It's already balanced. So in the first beaker, I'm going to have H plus and F minus floating around. And in the second one, I'm going to have Li plus and OH minus floating around. And in the last beaker, H2O is going to be the driving force of this reaction. And here I have Li plus floating around and F minus floating around. All right, let's balance the reaction here. In this case, again, we're going to make H2O. But because Mg is 2 plus and NO3 is 1 minus, it's going to look like that. And I'm going to do that to balance it. Okay, so in this case, I have 2 H pluses floating around and 2 NO3 minuses floating around. Here I have 1 Mg2 plus, but that's going to require 2 OHs minus. This is a proportion, by the way. So if we had 50 Mg2 pluses, there would be 25 OH minuses and vice versa. So again, here I have 1 Mg2 plus and the NO3 minuses. Then I have these 2 waters. All right, last one, HBr. Now be the H and the CO3. We know here we're going to make H2O plus CO2, and K is plus 1 and Br is minus 1. I'm going to balance that reaction by doing this. H plus, Br minus, plus, K plus, CO3 2 minus. Now this big beaker walks past me. Na 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 na. Ba na ba, ba na ba. And here we have a water and CO2, but that's bubbly. All right. Stage whether you agree or disagree with the statement below. Justify your answer. The boiling point of HBr is less than the boiling point of HCl. False. HBr and HCl are both polar molecules, okay, polar acids. So they both exhibit London dispersion and dipole-dipole forces. There's no H bonding in either of them either. So, because Br is a more polarizable atom than Cl, HBr exhibits stronger London dispersion forces and thus a higher boiling point as well.